So lastly, let's do A, B, and C of the second problem on the Relativity Lab Part 2. So in this one, you have Einstein, who, let's have a time coordinate and an x coordinate, and Einstein just sits there at Earth and doesn't move, while Newton flies out, stops, turns around, and comes back. I'm just going to calculate the first half of this. The total time and total distance will just be twice the answers that I find here. Either one is fine, just be very clear which time and distance you're talking about. So, in the problem, Newton flies at 4/5 the speed of light, and he flies for 10 years. The problem says that Newton flies out for 10 years and then turns around to come back. So it's 10 years in his frame that he perceives. So the first question is, how long does this time take from the perspective of Einstein, who is on Earth? Well, this is a time dilation problem. So what do we know about time dilation? We know that delta t prime is equal to gamma delta t naught. So this is the proper time. This is the dilated time. So in all these problems, you always want to determine who is the proper time, if it's present at all. So in this particular problem, remember that the definition of proper time is it's the time where, in the frame where two events happen in the same place. So from Newton's perspective, he leaves Earth, and then he's like, I'm going to go back. So from his perspective, both those events happen in the same place. They happen where he is. Whereas Einstein says Newton leaves, flies out, and then when he's way over there, he stops, turns around, and comes back. So Newton perceives the proper time. Einstein does not perceive the proper time. So first, let's calculate the gamma factor. So gamma is 1 over the square root of 1 minus v squared over c squared. V over c is 4/5. That's 1 minus 16/25, which is equal to 1 over the square root of 9/25, which is 5/3. So if Newton sees himself as taking 10 years, Einstein would perceive him as taking 50 divided by 3 years. So let's just keep a record of that delta t from Einstein's perspective is 50 over 3 years. Delta t from Newton is equal to 0. Sorry, is equal to 10 years. So next we can ask the question, how far does the trip take in Einstein's frame and in Newton's frame? So in Newton's frame, the trip doesn't take any distance at all. He leaves, he waits a while, he decides he's going to go back. From his perspective, Earth goes away from him, it stops, and it comes back to him. So he is in the same place for this entire trip. So for him, the trip is 0 distance. What about for Einstein? Well, for Einstein sees him traveling at 4/5 the speed of light for 50 years. So the distance that Einstein sees is just velocity times time. Velocity is 4/5 the speed of light times 50 divided by 3 years. So the total distance out that Newton travels is 40 divided by 3 light years. Remember that a light year is the distance that light travels in a year. So since distance is velocity times time, if you have the speed of light times a year, that is a light year. So I'm using c times year to represent a light year. So the distance that Einstein sees Newton go is 40/3 light years. So we now know how long the trip took in Newton's frame, how far he went in Newton's frame, how long it took in Einstein's frame, and how far he went in Einstein's frame. So we can calculate the invariant space-time intervals. So delta S which is c squared delta t squared minus delta x squared. So if the trip took 10 years for Newton, let's calculate for Newton first. That's c squared times 10 years squared, and had a distance of 0. Then we have 100 light years squared. What about for Einstein? Einstein says that the trip took 50 divided by 3 years and went a distance of 40 divided by 3 light years. So I can expand this all out. What do I have? 2,500 over 9 light years squared minus 1,600 over 9 light years squared. So if I take this difference, what do I get? I get 900 over 9 light years squared is equal to 100 light years squared. So again, they disagree on the time, they disagree on the space, but they agree on the invariant space-time interval, that it's 100 square light years.